Welcome to this webinar on electronic cooling and thermal management simulations using ANSYS ICEPAK. So in today's webinar, I will be giving you the basic fundamentals of electronics cooling and basically why electronic cooling is so important while designing the electronic devices or electronic gadgets. And then we'll be covering little bit of basics of heat transfer. So this course is basically I have designed for the students point of view as well as from the experienced person's point of view. So for students, I will just touch up a little basics on the heat transfer, and then we will go on the some part of the electrical and thermal analogy. Now, if you consider electrical circuit and the thermal circuit, both are kind of equivalent, and then I will be, correlating electrical fundamentals and thermal fundamentals, and you will be knowing more on the correlation parts, and then you will be learning more. So next topic I will cover is thermal simulation process. Computational fluid dynamics, we have certain process to follow. Similar process is there for doing the thermal analysis for the electronics. The thermal analysis of electronics is purely based on the CFD process, but in CFD we have general CFD codes where we use the different purpose. For the geometry purpose, we have CAD softwares. For the pre-processing, we have CFX and Fluent. For meshing, we have different softwares. So in general CFD, we have different tools, but in electronics cooling, we have only ICEPAK, which is integrated. So I'll take you through all the process which we follow in the thermal analysis. And when you consider the thermal analysis is based on at what level we want to do the thermal analysis. So we have chip or package level thermal analysis, we have board level, and we have system level. So I will give you a brief introduction about all these different levels of thermal analysis, and then we will conclude. So today's webinar is basically the introduction, and from the next class onwards, I will take you through the actual hands-on through the software. Then we will solve different kinds of problems. We will model actual modeling because in my career I have solved so many problems. I will take those kind of problems, not directly from the industry, but similar problems, and then we will try. Basically, why thermal analysis is so important in the electronics devices. If you consider the electronic device and its failure, so temperature is the major cause of component failure. Now, in every device, if you see in home, consider from the mobile, TV, fridge, or anything, if you see the every component releases heat, and so the temperature of the components goes up. Now, if you see the failures of these components from the analysis, it has shown that the components fails due to temperature cause. So 54% of electronic devices fails due to temperature. Then 20% fail due to vibration. 19% fail due to humidity. So if we consider, so temperature is the major cause of component failure. Now, many people might have observed in the news that there are fire in the mobile device bursted. So basically it is because of temperature, battery got overheated and battery got blasted. Now currently I'm in the wind industry, and in wind industry also, if we see, we have a lot of failures due to thermal issues. The nacelle got fire, and I have shown a picture where the wind turbine nacelle itself catch fire, and then there is a complete collapse of the turbine. So if we think the temperature is the major cause, because of temperature we have reduced reliability, and the components, if we consider, because there is a failure, there is a question on the reliability. So as a thermal analyst, we have to be very sure to solve all these problems. Again, the another thing is security concern, and day by day now, if we consider the electronics devices, the electronics devices are getting smarter. So we have more processing power. If we have more processing power, we have more heat. I will take you through different slides where we have trends in the electronics device. So we think of how the electronics designs in the future. I will take you through the next slide. There are again soft failures. Soft failure means the property change over the period of time because of the temperature. The properties of the material change. Even processor gets slower because of over heating. And then we have change in the performance of the system outside the specification of the design. So these are all the problems related to thermal, and that is where the thermal analysts come into picture, and there we are to solve the industry problem. So if somebody wants to know what is actually a thermal analysis, the thermal analysis is nothing but the temperature prediction using the CFD simulations or calculations. But the thermal analysis is purely depend on the inputs, and the inputs again we need to validate through certain tests. So when we do CFD analysis or the thermal analysis, here we don't mean to exclude the test. Again, when we do thermal analysis, we have certain criteria for the electrical design, the electronics design, and we have to do trade-off between the electrical and thermal trade-offs. So we have to do a temperature, cost, and design trade-offs. So in an industry, I would say we have a great opportunities as a thermal experts, and if we go deep into thermal analysis, so and if you become a thermal expert, you have a great opportunities. As I told, these are the trends in the electronic industry which poses the challenge for the thermal analysis. So if we consider, we are now using multiple chips on the single PCB board. So if chips modules are used on the single PCB, they releases more heat because of the more processing powers, and the devices become hot. We need to be very, very cautious. We use a plastic material nowadays for the packages. Here packages means once if you consider any processing chip, the processing chip is included in a package, plastic enclosure, and day by day these chips are getting reduced by size. Now if you consider the mobiles, earlier mobile chip were used to manufacture on 28 nanometer scale, and that becomes 24, and now 18 and 14 and even 10 nanometers chip sizes are available in mobile. So many people, if we consider the processors, when we compare the mobile specifications, we see how much nanometer scales these chips are made of. So we are reducing this size of the chips, and then we are inviting the thermal problems. We are miniaturizing the components. So if we think of the mobile, which used to be in 1995 when it got introduced, we used to have very bulky model, Nokia model. I still remember we had the black model. Nowadays, if we consider our mobiles, it is very slim and we are very sleek with more processing power. So again, it is related to getting more processing. Many industries, we eliminate fan to reduce noise, because fan is continuous operation of the forced convection, and because of that we have noise. So we eliminate fans to reduce noise, and we solve the problems using the conventional or convection natural convection system. We also design the equipments with more power dense systems, and we get problems. As I told, processing speed increases, so we get devices hot. So these are the trends which is going in last 10 years, and even in future we are going to see these trends, and then we get all the challenges related to thermal issues. So resolving heat flows in densely populated boards requires large and high fidelity models, and that is again became a challenge because we have to depend on a lot of network models. Now in future lectures you will see what is this network model means, and also we have to be very sure about the vendor which supplies this thermal resistances values. Now again, in next few slides I will introduce you to the thermal resistances, and then we'll talk more on this. Again, we have to consider the thermal interaction between the closed space powered components. So as I told, on the single PCB board, we have different multi-chips module, and which again become very difficult in the two point of view. One is electrical point of view, and the thermal point of view. Both has required, spacing. So, and then we have to design the PCB as well. So these are the trends in the electronics design, and which poses the challenge in thermal analysis. Now we understood that thermal analysis is how important it is, and then in the design process we have to be included this thermal analysis in pre-design phase itself, because if we include thermal analysis after all the design phases are over, like electronics and electrical design is over, PCB design is over, and then at last if we do thermal analysis, we will have very limited scope to change the design. So as a thermal analyst, we have to be included in very first pre-design phase, and then through this we can reduce number of prototypes to be built, number of tests to be built, and we can even save a lot of time, feasibility study for the evaluation of all these designs. Also during early phase itself, if we include all this, we have more scope to provide the cooling solutions, we have more scope to optimize the cost of the product, we have more scope to optimize overall temperature, and the time to market will be very less based on the where we do the thermal analysis. In my career, I have seen that people ask thermal analysis at very last stage just for the validation purpose, and literally we had no scope to change the design, and we have very limited time for the market to release the design, and then the product was very hot, and after the product was introduced in the market, again we got a lot of reliability cases where we need to solve those reliability problems. So it's better to include the thermal analysis in the early or pre-design phase, and we have to eliminate all the problems related to thermal design. So the objective of the thermal analysis is the prediction of the thermal performance and the design evaluation. So the objective of thermal design again changes based on where we include the thermal design. If the thermal design is for the reliability problem, then we do the thermal performance and then we make the corrections. If the thermal design is included in the pre-design phase, then there we have the design evaluation challenge. So the objective changes based on the where we are doing the thermal analysis. The another objective is as a thermal analyst, we very sure to eliminate higher junction temperature of the component. Now again, this junction temperature terminologies I will introduce you in the coming slides. But junction temperature is nothing but the temperature of any IC circuits, and when we design the PCBs, select the components, then we have certain maximum junction temperature limits as specified by the manufacturer, and when we design, we have to place these components on the PCB, and we have to take out the heat which is generated because of the processing power of these chips, and we have to eliminate the junction temperature. As if the component junction temperature becomes high, there is a possibility of failure, or there is a possibility of reduced processing. Again, we have to select the suitable cooling system based on the again design criteria, whether we have to use natural convection or the forced convection, or we can simply use some there are different cooling materials available, where the conduction we eliminate the heat, because of the conduction we put thermal insulations. So we have a lot of cooling solutions, so we have to select the suitable cooling solutions based on the outcome of the thermal analysis. Also we have to do the trade-off as I told, and we have to again consider the important design and the deployment consideration, how the product is going to be used after it reaches the market. Many times the product is designed for certain use, but the end user uses the product based on their wish, and then we face a little, because the voice of customer was not captured properly. So these are the problems which comes in the product design, and then in the thermal analysis we have to solve all these problems. Now once we know everything, so we have to understand the components, understand the nature of the thermal design. Now if we think of the any problem which is related to any equipment, now what happens in the electronic equipments, this is related to multi-faceted heat transfer subject. Now any electronics, this involves all the areas of heat transfer, such as conduction, convection, radiation, then the fluid flow, the pressure drop, the now use of extended surface for the cooling purpose, like heat sinks and fins. We have to use the experimental techniques to understand the nature of the heat transfer happening in the equipment. We have to use the empirical data analysis also as well, and we have to again depend on the suppliers, the network models for the chips. We have to do a numerical and computational methods, and we have to do heat exchanger design. So in any electronics, if we think, there are all types of heat transfer phenomena happening, the conduction, convection, radiation. Now consider a mobile. When the mobile is designed, there is mainly heat transfer happening because of the conduction and convection. There is little scope of radiation. So when we try to design any or do the thermal analysis of electronics, we have to properly think of physical phenomena, and then based on that we have to design the cooling system. As initially only I told, we are not doing thermal analysis and eliminating any test. There is no substitute for the experiments. So experiment is very much required for the validation of the thermal model, and based on the validation of thermal model, we have to take a next step. So validation tests are very much important, and in the design phase, whenever it is possible to conduct validation test, we have to do a validation test. Accurate thermal analysis prediction is difficult and becoming very a challenging task because of the complex geometries of the PCBs, processing chips, and the even equipment. We have non-uniform component sizes and layout, non-uniform board spacing, and heat dissipation. So when you consider any PCB, PCBs have number of layers. These number of layers are having positive current, having negative current, having grounding. Then there is circuits. So if we think of any electronic PCB design, it has number of layers, and we have non-uniform board spacings and the spacing of the components. So heat dissipation is non-uniform, and then it becomes very much difficult, and we have to do a design in hand with electrical or electronics engineer and solve this problem. If we consider any device, then again the natural convection becomes more difficult than the forced convection. In forced convection, we have more scope to provide the solution by using different fans, different flow rates. But in the natural convection solution, it is pretty much difficult to dissipate the heat because of the conduction. We have to have more conduction than the convection and the radiation. So accurate thermal modeling is critical, and in the design phase, we have to be very sure of all this. And if we have the proper input data, then we have the proper network models and proper thermal models, then it will be very much simple to design the to do the thermal analysis, and the results will also be more reliable. So selecting the right tools for the right purpose is very much important, and ICEPAK is kind of a tool which has a lot of features for the thermal design. It has a lot of macros. So I will take you through different slides where I will introduce the ICEPAK interface, and then we'll discuss more on that. This is the pretty much basic I have concluded in one slide. So there are different modes of heat transfer, mainly conduction, convection, radiation, and we have to connect these modes of heat transfer to the electronic components. Now in electronic components, we have heat generations because of the Joule heating, the trace heating. We have different phenomena. We'll take few slides on the heat generation, how the heat generation happens in the electronics. And now after generation of heat, we have different modes of heat transfer, the convection, conduction, and radiation. And we have to dissipate these heats with all these modes of heat transfer. So I will not go through in detail because I believe that everybody knows basics of heat transfer. So these are the, before trying to solve any problems, we have to have strong fundamentals, and we have to have strong knowledge in the heat transfer. So for example, if we see, now we have electrical cables connected to electrical device. So both the components are source of heat, and when both the components interact with each other, we have to understand from where the heat will flow, and from the cable to device or from the device to cable. Again, it depends on how much heat is generated in both the device. At the same time, if the device is generating more heat, the cable will be act as a thermal conductor for the conduction of heat from the device to cable. And from cable, the convection will occur or radiation will occur, and the heat will be dissipated. Now, when we consider the modeling of this kind of phenomenon, now we cannot have cable length modeling more than infinite, more than 1 meter. It is depend. So what happens? We need to isolate the cable, do the cable modeling analysis, and then the equivalent boundary conditions we have to put on the cable end to draw the same amount of heat.